In this tutorial, we're going to take a look at three examples of using the primary trig ratios in right-angled triangles to solve some problems. So this is the first of the three examples. Beth wants to know how high the flagpole is in the front of her school. So the flagpole will be this BC side here. That's the flagpole. And it's too tall for her to measure directly, but the sun is out and she measures the shadow length to be 6.5 meters. So this would be, when I draw my triangle, this would be my 6.5 meters across the bottom here. That's on the ground. That's the length of the shadow. The shadow is actually on the ground. And the angle of elevation from the tip. So if she goes here and measures the angle of elevation right up to the top of the pole, like that's the tip of the shadow on the ground, and she measures that to be 61 degrees. And the question is, how high or how tall is the flagpole? So we know this side and of course the 61 degree angle. So let's label sides here. So in relation to the 61 degree angle, this would be the adjacent side here. And the 61, you see straight out across from it is the little A side here, which is the flagpole, and that would be the opposite side. So those are the two sides that we're working with, opposite and adjacent. And opposite and adjacent, SOHCAHTOA, that's the TOA on the end, that's tan. So we're going to use the tan ratio here because we're working with we're trying to find the opposite side and we know the adjacent. So filling in the values, the angle is 61 degrees. The opposite side I'm calling A here, and the adjacent is the 6.5 shadow length on the bottom. Now, in order to cross multiply and solve for A here, the tan 61, think of that as tan of 61 over 1. So when I cross multiply, A times 1, which would just be A, would equal the product of 6.5 times tan of 61. So in my calculator, bring my calculator over here, and whenever you're doing a trigonometry, make sure your angles are your calculator is in the right mode. So if I go in this one to mode, it measures angles in radians and degrees both. It works with both. So I want this to be in degrees because that's degrees there. So it's 6.5 times the tan of 61 degrees. So that's the 11.7 that I'm going to get here. So let's move the calculator across here. So that's where I get my 11.7 meters. So that's how tall the flagpole is. It's about 11.7 meters tall. Example number 2. Sam walks from his home 2.5 kilometers north. So the H represents home here. So he's going 2.5 kilometers north. We normally, on paper, represent north as up the page. So he's walking across this frozen lake. And then he turns when he gets to point J here. And he walks another 1.4 kilometers west. So this is why I would draw a side over here, 1.4 kilometers west. West is normally indicated by to the left. And so he's right here at K, and this ice fog settles over the lake, so we can no longer see his house. But he has a compass. So we're asked to tell him two things: how far he needs to walk to go directly home, and the direction he needs to take to go directly home. Now, we don't need trigonometry to find the distance KH here. We know two sides in the triangle, that's a right angle. So if we know two sides in a right triangle, we can use Pythagoras' theorem to find the third side. And the KH would be the longest side. That's the hypotenuse in the triangle. It's because it's across from the right angle. So the KH side squared would equal 1.4 squared plus 2.5 squared. So let's bring the calculator back here. So I'm going to square 1.4. That's 1.96, and then also 2.5. We'll square that. And then we're going to add those. So 1.96 plus the 6.25. So when I evaluate these and add them, that's what KH squared is going to equal. So 8.21. So let's do that. So KH squared is 8.21. Now, in order to find the KH side, we get rid of the square by taking the square root. Remember, square and square root are opposite operations. That's why in lots of calculators, one's on the function key, and the second one's like the second, that same key. So I'll go second, my square root, and then 8.21. So about 2.9 is the length of KH. So that's how far he needs to walk home. Now we need to tell him a direction, and we do need some trigonometry for that. So the direction, of course, on the diagram, the direction is along this dotted line, but you can't say, well, walk along the dotted line, Sam. So what we're going to do is we're going to find this angle here. And I guess I did the tan there a little bit prematurely. In this triangle, for the K angle, this one right here, this would be the adjacent side because it's right beside the K angle, and straight out from it, the 2.5 would be the opposite side. So that's why we're using tan again. So and of course it's K we're finding, so it's tan of K. And the opposite is the 2.5, and the adjacent is the 1.4 sides. Let's bring the calculator back again, and we'll want to divide 2.5 by the 1.4. So that's what tan K will equal. And I rounded to I always round to 4 decimal places. Don't round too quickly. If you go 1.8, for example, if you rounded that to 1.8, then your angle could be off by a degree or two. So keep several decimal places to maintain accuracy. So the way we find the angle now is we go second tan, and we want the inverse tan or arctan function of that 1.7857 number. So 60.75, which of course would round to about 61 degrees. So this angle right here, and let me get rid of my writings. This angle right here would be 61 degrees. So I'm going to put 61 in here. And I just put this compass image here. One way to tell somebody a direction is to use something called a bearing. So this compass, see, that's the N stands for north. So straight north is straight up the page. And then as we rotate around, see, that would be straight east. See the E right there? That's called a bearing of 90 degrees. And if we go another 90 degrees, that would be 180. So that's straight south. So bearings are angles from, it's called true north, rotated around. So you see, around to east here is 90, and then we have 61 more degrees. So the bearing around to here, around to that dotted line, would be 90 plus 61, which is 151 degrees. So he's walking 2.9 kilometers home, and he would be walking in a bearing of 151 degrees. So we could take his compass and then use the compass so that he could walk exactly along that dotted line and get directly home. In example 3, Danny is flying in a helicopter 800 meters above a flat plane, so D represents where Danny is. So when I draw this triangle, I would have this vertical side, that's 800 meters, he's above the ground, above the flat plane. And he sees this moose at an angle of depression of 20 degrees. So here's his line of sight, so he sees the moose. The moose is at M. And the angle of depression is with this horizontal line, which is his flight path, and his line of sight. And remember, angle of depression is the same as angle of elevation. If you were the moose looking up at Danny, then this would also be 20 degrees here. Now, in the triangle, let's label sides, we're working with this 20 degree angle, so straight across from it is the 800 side, so this would be called the opposite side. And we're asked to find how far away the moose is from a helicopter, so that would be the length of this dotted line here, and that would be the hypotenuse side, because that's straight out from the right angle. So we're working with opposite and hypotenuse, which is the sine ratio. The first part of SOHCAHTOA, the SOH, sine is of an angle is opposite over equals opposite over hypotenuse. So let's fill in the values. So we're working with this 20-degree angle. The opposite side is the 800, and we're trying to find the hypotenuse, which is the DM side. That's what I'm calling it here. So if we write the sine of 20 as sine 20 over 1, we can cross multiply. So 800 times 1, which is 800, would equal the product of the dm and the sine of 20. Now I'm trying to isolate for dm, so I would divide out the sine of 20 from both sides because I want to get the dm alone. So the sine 20's divide out, so dm is equal to 800 divided by the sine of 20. So that's the calculation, and I'll bring my calculator back here again. So 800 divided by the sine of 20 degrees is 2339. So that's the distance Danny is away from the moose at that instant in time. So the moose is about 2,339 meters from him, or about 2.3 kilometers. Remember, we convert from meters to kilometers by dividing by 1,000, because there's 1,000 meters in a kilometer. So he's about 2.3 kilometers from the moose. So that's where the 2.3 comes from. And that's the end of the tutorial.